Hello, this is Philip and welcome to my channel for this new episode of kOS. We are here in Kerbin's orbit with that little probe, and today we're going to talk about functions, and more specifically about the return statement of a function. Until now we saw that a function could be used as a shortcut, if you want. For example, that function start countdown, it's just a way to encapsulate the script here. So writing here start countdown, it's just a mean to say to kOS, okay, run that part of the script. And it is easier for us to write a script like that, because if I have multiple missions, I can just write start countdown each time, and each time this will be that part of the script. This part of the script will be executed by kOS. And in function we can have parameters or no. Okay, there are some. This is a parameter. This is an optional parameter, and this is a mandatory parameter. Okay, but today we are going to look deeply in the very nature of a function. It is not a simple notion in informatics. We are just to look at the surface of what is a function, and if you don't understand anything, be free to ask your question in the comment section. To understand what is the return statement of a function, I wish to use an example, not a simple example. This is a specific example, and I chose to talk about that example because it's a very useful example in KSP if you want to write scripts to launch rockets with kOS. Imagine you need the velocity of your craft. So this is your craft in an elliptical orbit. Okay, so your craft is orbiting around Kerbin. In the real world, the altitude of the craft is measured from the center of mass of Kerbin, and the periapsis and the apoapsis of the orbit are given from the center too. In KSP world, it doesn't work exactly like that. The altitude, periapsis, and apoapsis are given from the surface. And this is the first point you have to understand. The formula here is the formula that gives you the velocity of your craft at any altitude. Mu is called the gravitational parameter of Kerbin, of any planet. It's a big number, but don't worry, kOS knows that number, because kOS is capable of searching in the folders in all the files of KSP to pick up that number. A is the semi-major axis. The major axis of an ellipse is here that segment line from the periapsis to the apoapsis. The minor axis is the perpendicular of that line. And the semi-major axis is the length of the major axis divided by 2. So if I want to calculate the semi-major axis, I have to add the apoapsis with the periapsis, and then I have to divide by 2. This is the real formula in the real world. In KSP, the value of the apoapsis is not exactly the real value of the apoapsis. This apoapsis here is equal to the radius plus the length from the surface of Kerbin to that point. And for KSP, this is the apoapsis. So if I want to use that formula in KSP, I have to add the radius and the apoapsis. I won't explain that formula. If you wish to know more about the mathematics behind the scene, behind KSP, you can watch at Mike Eben's channel. It's a great channel with a lot of contents, and Mike did a tutorial, a math tutorial, a math series, not real tutorial, but a math series called Let's Do the Math, and he explained in that series a lot of formula useful for KSP, and useful if you want to create complex script with kOS. Okay, so just imagine that you have found that formula and you want to integrate it into your script. The better way to do that is to create a function. In my script folder, in my lib folder, I will create a new library. I can call it, I don't know, maybe orbit calculations and .ks. And here I will create my new function. This is a global function. So that global function is compute velocity, compute vel. Let's say that. It needs 3 parameters. The first parameter is the periapsis, the second one the apoapsis, and then the ship altitude. Okay. If you look at the formula, we need the gravitational parameter mu. Let's create a variable, a global variable. Let's say b mu. B is for body, and mu, yes, it's a symbol. Mu, it's that symbol. Okay, this Greek letter is called mu. All right. So local mu is ship body, and there is a suffix mu. So you don't need to know the exact value of that number. kOS knows it for you. Okay, we need the altitude of our ship, but the altitude of our ship, so local SA for ship altitude, is the parameter ship alt. But if I just write this, it is the ship altitude for KSP, that means from the surface of Kerbin. And in the real formula, in the real world, I want that formula, I want the altitude from the center of Kerbin. That means I have to add, at ship altitude, I have to add the radius of Kerbin. I have to add the radius of the ship's body. And that number is also known by kOS. I prefer to write body instead of Kerbin directly, because I want that formula to works anywhere. If I am in orbit around Minmus or around Duna, I want the formula to work everywhere. Okay. Instead of ship body radius, let's create a variable local b radius. So is the body's radius. I don't have to do that, but I prefer. Okay, then I need the semi-major axis. So I need the local RP for radius plus periapsis. So this is the radius plus the periapsis, and the periapsis is the parameter pair here. I need the same for the apoapsis. So local RA is the radius of the body plus the apoapsis, right? And then I need the semi-major axis, and this is RP plus RA divided by 2. Okay, I have all I need. Now I can just write a local velocity is and write my formula. So the square root symbol, the square root is SQRT, okay, square root, the square root of mu multiplied by the rest. So mu is B mu. Okay, I want to multiply this by 2 divided by the altitude, so 2 divided by SA, the ship altitude, plus, no, not plus, minus 1 divided by the semi-major axis. Okay, but I won't do that, because this is the result I want. If I am using that function, I want that number. I want the function to return to me that number. I don't care about all the calculations here. I only want the result. So I want the function to return that number. And that is all that matters. Okay, and one thing very important is that the return indicates to the function, okay, that is the end of the definition. I can't write anything after a return. It won't be used by the function. As soon as the function has a return statement, this is the end of the function, and that function returns that number. Okay, so now I want to use it, right? So let's go to my test function here. I must add the library orbit calculations. And I don't need this anymore. I just want to print my actual velocity. Let's create a function, set actual velocity is, and I want to use so compute velocity. So I have my probe in orbit, and I want to calculate set actual velocity to compute velocity. I want to calculate its velocity. For this, in my function, I need 3 parameters: the periapsis, the apoapsis, and the ship altitude. So here I just have to write ship orbit periapsis, the ship orbit apoapsis, and here periapsis, ship orbit apoapsis, and the ship altitude. And here I just want to print actual velocity, and this is a number. It will be a big number, so I will run it with only 1 digit in the decimal port. Okay, the problem, it's not for compute velocity, because compute velocity doesn't exist. It's compute vel. So let me call that velocity. Maybe it is more adequate. Okay, let's go back to our probe in orbit. Okay, so the velocity I want is this one. Okay, so run path 0 missions tests. That should be better. Okay, you see the velocity 1775.4. That was the velocity here when I have executed the script. Let's do this again and look quickly at the number that is here and the number calculated. Let's go 3, 2, 1 now. Up, You see, this is the same number. So that works. This is a good news. So what happens exactly? I create a new. I created a new variable, actual vel, for actual velocity. That variable is set to something. The something is the result of that function. And the result of that function is given by the return statement. Here I have return a number. So my variable here is set to the number here. And then I have to print the variable. Okay, so this is not the same use of a function that the function start countdown. Start countdown is a function that just copy paste, if you want, the script here. In that function with a return, kOS will use all of this to calculate that number, and it will return only the number calculated, and not all of this. I hope you understand. That function can calculate the velocity of my ship in every situation. This is the actual situation of my ship. The periapsis is actually that, the apoapsis is actually that number, and the altitude is actually that number. But I can calculate the velocity of my ship in other configurations. Let me explain. Here we have an elliptical orbit. And you know, it's sometimes better to have a circular orbit. Okay, that means that in a circular orbit, the orbit is a circle, and in a circle, the apoapsis and the periapsis are the same. Okay, so that means, for example, I want to circularize my orbit from the apoapsis. So I have a velocity here. When my craft is at the apoapsis, I have a velocity. Okay, and I want to calculate what should be the velocity of my ship if the orbit were circular. Okay, so let's do the example right now. I hope it will be clear in any seconds. So this is my actual velocity. I want my velocity, so compute velocity. I want a circular orbit. That means that my periapsis must be equal to my actual apoapsis. Okay, and I want to compute that velocity at the moment where my ship is exactly at the apoapsis. And you see that? So I want a circular orbit. That means that the periapsis is equal to the apoapsis. That's why I have two times here apoapsis and apoapsis. And I want to compute that number when my ship is exactly at the apoapsis here. Okay. And the actual velocity is the velocity using that orbit, but when my ship is also at the apoapsis. And the purpose of this is to compare the two numbers. Okay, so I want here not ship altitude, I want ship apoapsis. Okay, and the objective of that is to calculate my delta V needed to circularize the orbit at the apoapsis. And circularization at apoapsis. Okay, so print the actual velocity, and then I want to print the wanted velocity. All right, and I want then to calculate the delta V. So I want to print that number, the wanted velocity, minus the actual velocity. Let's try. Okay, circularization at AP. So when I reach the AP 362.8 is the velocity of my ship. I want to circularize, so I want to have velocity equals to 758.7. For this, the delta V needed is the subtraction of these two numbers, 395.9. I don't have enough delta V, but it doesn't matter for the exercise we are going to do. So let's go to the map view. I want to go to the apoapsis, and we'll see my velocity is decreasing, okay, because I'm being very high in the orbit, and you see I'm nearly at, I'm searching the sun for a good light for you. You see the velocity here. I'm 7 minutes until the apoapsis, and my actual velocity is 364 meters per second, and the calculation said that my velocity will be 362.8 at the exact point of the apoapsis. Now I want to create a node here in the apoapsis. Just add another node, and I won't create it manually. I want to put that number 395.9 here in that command. I know that I need to burn prograde, and the delta V is 395.9. Enter. And you see, I have here a very circular orbit. Okay, the apoapsis is here and the periapsis is here. Okay, it is not perfect. You can see that the apoapsis is 5,535,628 and the periapsis is not exactly the same number, because I create the maneuver node manually, and the maneuver node is not exactly, if I zoom in, you see, it's not exactly at the apoapsis. And that's why I need kOS to compute the exact delta V needed to create my circular orbit, and to create the maneuver node at the exact point of the apoapsis. Okay. Okay, so this is for the circulation in the apoapsis. If I want to circularize from the periapsis, I can use my function again and the return statement to compute all that numbers. Okay, so let me delete. Okay, now imagine, so you want to circularize at the periapsis. For this, the actual velocity is the velocity with your actual orbit, meaning with the actual periapsis and the actual apoapsis, but this time you want to burn at the periapsis, so you want your ship to be at the periapsis. Okay, so you want this velocity to be computed at the periapsis, and the wanted velocity, this time you want to circularize at the periapsis. That means that the periapsis is the same, but this time the apoapsis must be equal to your periapsis, because you want to have a circular orbit at the periapsis. So the apoapsis must be equal to the periapsis, and because you are doing your burn at the periapsis, here you have to write periapsis. Okay, and here I don't need to change anything. Let's try it. Okay, I'm now close to my periapsis, and I can run my script. Okay, circularization at periapsis. My velocity will be 2810. We are close to that. I want to, because I want to lower my apoapsis. Okay, so I want to lower the speed of my craft. So the actual velocity will be 2,800. I want to slow my craft to 2,112 meters per second. That means the delta V needed is negative. And that means if the delta V is negative, I have to burn retrograde. And if you know KSP, if you know how it works manually, you know that you have to burn retrograde to lower your apoapsis. So this time, let me create a maneuver node here. And the value of the delta V here must be negative 698.9. And you see, you have a circular orbit. After the maneuver, you see that the apoapsis is quite equal to my periapsis. Not exactly, because I didn't put the maneuver node exactly at the good spot. Okay, that's all for today. It was a very specific episode because it was a very specific example of the use of the return statement for a function. I hope you understand it, and I hope when I'm going to use a more example of that kind of function, it will be clear for you the way I use it. Okay, so I want to thank you for watching, and see you soon for the next episode. Bye bye.